before, this idea of motive, around maybe 80, 90 years ago, Weil, mathematician, he kind of came up with some conjectures around counting points over a finite field over some curve, on some curve or some surface. This was kind of before even scheme theory in the sense of SGA was kind of formalized. So it was still kind of the Italian school of geometry, where it wasn't really sheaf theoretic or functor theoretic terms. It was more just maybe, well, I don't know. I don't know how Italians kind of formalized geometry, but it was certainly before functors were introduced to set up scheme theory, let's say. And so Weil was, if you have some kind of polynomial over the field of finite called Fp, for example, you want to count the number of solutions modulo P. Is a very natural question. It's just a Diophantine equation, and it has some geometric flavor. I mean, you can make a curve out of it, and you can frame it in terms of geometry. And that's what Weil was interested in. And he ended up proving it for, his conjecture was for any dimension polynomials, but he ended up proving it for curves only. And his idea was another mathematician called Grothendieck, Alexander Grothendieck in France, who was revolutionizing, who went on to revolutionize scheme theory. I mean, in terms of the language of functors. He took Weil's proof for the case of a curve, which we'll go through this lecture, and wanted to extend it to other dimensions. And the missing kind of key to extend it to other dimensions was this idea of a motive. So I think in this lecture we'll go through Weil's original argument for his conjectures for the case of a curve, and see kind of where this hidden motive or hidden idea of a motive lies within his argument. I'll point it out at some points, at some places. It would be nice, I guess, if people had some idea of like what a divisor is, or in the sense of maybe Hartshorne chapters, section 2, chapter 6, for instance, or something like that. If not, like it's not. You please email me, and we can I can even organize like a one-on-one or whatever outside of lectures, and I can explain kind of what a divisor is. At least, I mean, it would be nice to have, because I don't really want to go through that in lectures too much. Okay, so let me read kind of what I've written here. So Grothendieck, having read Weil's proof for the case of a curve of some conjecture, which I'll state in a moment, he sent a letter to Serre in 1964 detailing his idea for what a motive should be. So you can find this letter in this the annex of Serre's notes in this reference. It's written in French. So before we get into motive, let's have a look at what exactly the Weil conjectures are. So as I mentioned, in around 80 years ago or so, Weil was interested in studying the number of solutions of equations over finite fields, and he formulated the following conjecture. So this is his conjecture, written maybe in modern language. I mean, as I said, like there was no, there was notions of varieties, but maybe not in the sense of what your definition of variety would be, I guess. So let X be a smooth projective variety over Fp. Let's just ignore this technicality for now. Then one can define a so-called zeta function. So the zeta function basically so think of X as basically just a polynomial over Fp, and in degree n, let's say. And the zeta function basically, you're interested in counting the number of solutions modulo Fp of this polynomial, which is this number here. And it's natural in combinatorics to encode all that information into one generating function. So that's what the zeta function is. And he noticed through some experimentation, I guess, I'm not sure exactly like how he came up with this. I can explain like where this comes from now, having seen the machinery, but how he came up with this, I'm not sure, but I think it's through experimentation. So he formulated precisely like what this generating function looks like. So the first conjecture is the following. So there are polynomials from P1 to P2n minus 1 in integers, over the integers. such that each polynomial factorizes as as follows, where it's just complex factorization. There's nothing strange about that. But the crucial thing is that each coefficient here has a certain modulus, which is looking quite special, I guess. And then once you have these polynomials, the zeta function looks like some kind of fixed point or quotient of these polynomials. I guess in modern language, I mean, this is related to Lefschetz fixed point theorem, or the Lefschetz standard conjecture, at least. I mean, we'll get to the so-called standard conjectures in motives, but there is something called the standard conjectures by Grothendieck came up with, and one of the standard conjectures is called this Lefschetz standard conjecture, and this is very much related to the form of writing this zeta function like this. And this is called rationality, the rationality part, and the Riemann hypothesis part is this statement about the modulus being some special weight. And this statement is related to the so-called Hodge standard conjecture in terms of in the language of standard conjectures, which is about somehow this a certain involution being positive definite on some motive or something. And we'll see like an involution appearing here at some point in the proof. And then the second part of the conjecture is that if x actually comes from some variety, some integral lift, modulo p, some smooth integral lift, then if you look at the integral lift over the complex numbers, you can calculate its singular cohomology. Then these I guess, yeah, the number of terms here in each of these pi is related to the dimension of the singular cohomology groups. I guess in modern language, what this is saying is that is some kind of a comparison theorem between étale cohomology and singular cohomology. So, so it's actually this conjecture. I mean, not only did it give rise to this idea of motives, but it also is the reason that étale cohomology was formalized for schemes as some kind of singular cohomology version, algebraic version, I guess. A singular cohomology, of course, comes from topology, while étale cohomology is the algebraic version of it. And this is essentially this statement too. Okay, maybe like a quick example, which you can easily do yourself. If x is just a point, then there's only one rational point everywhere. And so the generating function looks like this. And if x is the projective line, then you have two coordinates a, b. One of the coordinates, if one of the coordinates is 0, you get PM solutions, and then the other one, the infinity point, basically is +1. And then, well, flipping the coordinates, sorry, having 1, 0, and the other 0. And then in this case, the generating function looks like that. So anyway, I mean, in these cases, you can check easily that the conjecture holds. So as I mentioned, like the Wahl conjectures, they are basically statements about étale cohomology. I mean, this statement here is basically some fixed point. Frobenius acts on this étale cohomology, and this rationality statement is basically giving information about the fixed point of Frobenius on the action of the étale cohomology of x. So there is a kind of smooth analog of Wahl's conjecture for Kähler manifolds, which was given by Serre. And in this case, the conjecture easily follows, not easily, but essentially follows from complex Hodge theory. While the Wahl conjectures, yeah, as I said, it's essentially étale cohomology. However, étale cohomology is somehow not strong enough, and that's where motives come in. Like you need to prove the Wahl conjectures, especially in particular this Riemann hypothesis statement. You need étale cohomology plus a bit more, and that a bit more is either in modern language, let's say motive, or in the language that Wahl set up his proof. It's Riemann-Roch theorem over the product x cross x times x, or as the version of the proof that we'll see, it's more intersection theory, which is, well, I chose it because it's more kind of conceptually closer to what a motive is. So I guess the moral of the story is that like over the complex numbers, you have Hodge theory, which is strong enough to give some kind of intersection theory, while on the algebraic side, or over finite fields, you have Italca homology, but it's not strong enough to understand intersection theory. So intersection theory needs to be taken care of. It's kind of extra work, and that's what a motive is essentially. So at this point, it's good to think of a motive as kind of Italca homology. It's basically Hodge theory minus Italca homology, the gap from Italca homology to Hodge theory in some sense. Okay, so Weil proved these conjectures for the case of a curve a year earlier in this paper, and his proof relies on constructing a suitable object from X, which is, well, what we now call a pure motive, but we'll see in this lecture is basically looking at divisors on the self-product of X and proving it has desirable properties. So let's look at the proof. It's not Weil's like original argument. Weil's original argument in this paper was essentially applying Riemann-Roch to the product X times X, but I'll be not using Riemann-Roch and doing more intersection theory. So, which is, as I mentioned, conceptually closer to motive ideas, in my opinion. Okay, so by the way, like if there's any questions, I'm not very good with chat or anything, so I'm not sure. Let me just check if people have written anything. No, but if there's any questions or anything or something's unclear, please like stop me right away or speak up, please. Okay, so let's have a look at some of the ideas in the proof. And that'll be basically the rest of the lecture. Hopefully it'll give some idea of like why a motive, where a motive is coming into this proof. Okay, so first of all, X was originally over FP, but I'm going to just denote X by what you get over FP bar. So I'll denote the original X by X naught. So let's relabel X by X naught and now use X to denote the base change. And as I mentioned several times, like we're going to look at the diagonal product or the twofold product, and we'll look at X times X. So a motive is essentially capturing the divisors of Y being X times X. Of course, there won't be any language of motives in the presentation that I give, but yeah, this is where a motive comes. This is where a motive will be essentially. Firstly, there's going to be I guess to keep in mind so that it doesn't look completely random is that we want to get an expression for we want to count the number of points, right, on the curve modulo PM, and this will essentially be like the number of intersection points between two curves on Y. So we're going to construct two curves on Y, and we're going to take their product, or their product meaning the number of points that they intersect at, and those number of points will be this quantity, and that'll give us like some handle on how to deal with this, because then we can use kind of the structure of intersection products to our advantage. So I hope that's clear. The way we're going to construct these divisors or these curves, which capture these two curves, which capture the number of intersection points, is going to be through actions of Frobenius, which is, not so surprising since we're working over FP. So, let's donate by phi the Frobenius morphism, which is basically an identity on the topological space, and on the algebra, it's just Pth power. And the first thing is that on the algebraic closure, the number of points, so all the points, basically XFP bar is basically all these points varying across all M. There's two actions. There's one action that's coming from the Frobenius on X, and there's one action that's coming from the Galois action or the Frobenius on FP bar itself. And these two actions are the same. And it's kind of like an easy commutative diagram chase. So I've left it as an exercise in the spirit of like homework exercise. But probably, as I said, like we won't do homework exercises unless people want to do that. And please send me an email if you do. Do it for fun, but please don't worry so much about not doing it, I guess. The divisors, the two curves that we're going to construct, one of them will be coming from the diagonal morphism, so x to y, y being x times x, and the other one will be the graph of the Frobenius morphism. So basically, we're looking at the diagonal, which is a curve on y, and the graph given by the Frobenius morphism, which is kind of the twisted diagonal of these things, and we're going to intersect them, and the number of intersection points will be this thing. And then we're going to do some algebra to kind of get a handle on how to reduce this down. So let delta x be the diagonal morphism, and let gamma of, so frx will be the Frobenius on the algebraic closure, and frx to the n will be its composite n times, and this gives a graph or a divisor or a curve on y, right? I hope that's clear. If it's not, please say so, and I'll explain more. So yeah, in this case, both the diagonal, x is of dimension 1, y is of dimension 2. So the x to y is a closed immersion. It's and it views x as a curve on y in y. And similarly, frx, gamma frx, or the graph of the Frobenius, also gives another curve. And so these are closed immersions and cut out divisors in y, or curves. And we want to eventually get to counting the number of points where they intersect, and they will intersect at exactly the cardinality of this term here. So let's try to get there. So first of all, I mean, there is a notion of like how to pull back divisors. Basically, what's happening here is delta x, it's a closed immersion. So that gives, on the level of algebras, that gives some kernel. So this is, think of it as the algebra or the kernel appearing here. And then we're kind of pulling that kernel back along Frobenius. And what I'm saying is that that gives the kernel corresponding to the closed immersion of the graph of Frobenius. And if you work at the level of algebras, it's really clear. So let's try and do it as slowly as I can, as possible. So first of all, by functoriality, the pullback composed with n times is just, well, it composes, well, yeah, I mean, n and pullback kind of, commute. So that's by functoriality. And then if it's enough to just think of, given an arbitrary endomorphism, in this case, we're dealing with Frobenius, but given an arbitrary one, we want to check whether the pullback of morphism along the arbitrary morphism crossed with the identity on the second component gives the graph. So I've written in Word like what's going on, but I guess, it's easier just to see it on the level of algebra. So for example, the diagonal morphism here looks like, on the level of algebras, it's just the tensor product of A with itself over A, and it sends A tensor B to the product AB. And then on the other hand, like the graph of some morphism phi, so the diagonal delta x, it's the graph of the identity morphism, right? In general, the graph of an endomorphism will still take the same shape, but it sends xy, x tensor y to the phi xy, where this is on the level of algebras. So once you understand that, I mean, that's just definition, essentially, of what the induced morphism is on the level of algebras, then it's clear, like, what is happening here. I mean, all I'm saying is that, like, the point xx gets mapped to phi xx, and that's what this statement is. But maybe I've written it in words a bit too much, but on the level of algebras, it's very clear. If it's not, please send me an email and we can discuss one-on-one. Okay, so I think we're happy with this statement, or if not, then let's just take it for granted, or let's just assume it. So now, as I've been alluding to, I want to get a handle on the cardinality on the number of points with the intersection number. So there is like a formal definition of intersection number. I will define it later on, like in the next lecture. But for now, like what's happening here is that like we're essentially counting the number of points so that they intersect. And that's because the intersection here is so-called transversal. And the reason that it's transversal is that the differential of Frobenius vanishes because we're in characteristic P. So for instance, like a basis for this divisor would be like AA, while this would be A and comma A to the power of P. But because the differential vanishes, the total tangent space here, it spans the tangent space at the entire of all of Y at that point. So the intersection is transversal. So this intersection number, although the formal definition is complicated, because the intersection is transversal, we're just counting points. So the question is like, is the number of closed points that they intersect at equal to this cardinality? I said closed there. I mean, that's a technical point related to the fact that I mentioned that let's not worry that I said this assumption that this is irreducible, but let's not worry about that too much. So in any case, like we want to count the number of closed points, which if you're not getting like all of this, or it seems a little bit too flimsy, then that's okay as well, because it's just the first lecture. And in the second lecture, like I will, spend more time maybe on the definition of where we want to go. But at this point, like the first lecture, just to give it a flavor of like what a motive is. But you should have, yeah, sure.
Like about notation. So like if you go up a bit, so like this square brackets, it seems like sometimes they mean a divisor, but okay, here, like in lemma 1.5, what do you mean like by, is it a divisor to the power n? So is it a self-intersecting or what is it?
Okay. So here I'm viewing like this as a divisor. And so this is also a divisor, and this is a map and on schemes, let's say. And now like this map on schemes or
this,
the pullback.
This pullback n times.
Yeah, sure. Yeah.
That's why the square brackets mean like two different things here, essentially. That's what my question.
Yeah, I mean, let's not. Yeah, exactly. Like this square bracket, like is not like having much information. It's just to separate the n from the star. But
okay.
in any case, like what's happening here is that like there is a notion of pullback on divisors, and that's what's happening here. I'm just pulling back the map n times on this divisor, basically.
Yeah, thank you. That's what I guess. Just wanted to clarify the notations. Thank you.
Sure. Thank you. Okay, so I've written the proof here, but let me try and convince you just basically why this lemma is true. So basically you're counting the number of intersection points of this guy, and the number of intersection points is basically, delta x, like it's basically intersection, the points look like xx, and gamma f r xn, the points look like basically x to the power of p. So something like that. Is that here we're taking, it should be clear straight away, but there is one subtlety, which is here where the action is on the Frobenius of x, while here fpn is kind of the fixed points of the Galois action on fp bar in some sense. So you have to match up these actions, and that's the point of this exercise here, where I said that these two actions match up. So I think this lemma is pretty clear. So from the explanation that I gave, I hope. So let's not go into like where I've written too much. Okay, like one subtlety maybe I should mention is that since we're counting closed points, like, officially you need to use like Hilbert-Null-Stellensatz to see that the closed points on x times x, which is y, is just x fp bar times x fp bar. But I think that's clear. It's not clear, but it's traditional. Thanks to Hilbert-Null-Stellensatz. So at this point, like we have two divisors, one of the graph of the Frobenius and one on the diagonal, and the number of points at which they intersect are in y times y. So this is in x times x, which is kind of the motive. So this intersection product is happening like on the motive on x, or in this case, like in simple language, x times x. So in what I'm saying is that to get this statement, like we need to pass through the motive or pass to x times x. In Waals' original argument, he was doing not so much intersection theory, but getting an equality like this via Riemann-Roch, which is also possible. So now to finish off or get towards the end of the proof, we need to more information on, so we've translated the information of the size of this thing, which is kind of what this conjecture is about, to something that's happening kind of on the algebra level of intersection products. So there's an algebra of divisors, let's say, or a group or of divisors, and there's a product on this group which is given by intersection product. So we need to understand now, well, if we want to take this route and make the solution work, we need to understand how the algebra underlying intersection products. So that's where the second or the last part of the proof is heading towards. And for that, we need to define this notion of numerical equivalence. Maybe it looks left field a little bit, I guess, for the first time. I agree, because also for me, like, it's not clear like why we should consider such thing. But I mean, if you're patient, then maybe we can see that. Maybe I can convince you that it works at least. But I hope I've convinced you that like we should start understanding the algebra of intersection products somehow to understand this better, thanks to this lemma. To do that, we need to somehow kind of like linear equivalence, or how divisors are made is basically through, saying a divisor is 0 if it's the divisor of a rational function, and that's linear equivalence. And somehow linear equivalence is, it's not strong enough to say something about the finite dimensionality of intersection products, let me say at this point. And that's why we need to consider another equivalence relation. So again, like divisors have a standard notion of equivalence called linear equivalence, which says that like a divisor is 0 if it's the divisor of a rational function. But that's not enough for us to study this algebra of intersection products. And we need to consider another equivalence relation, a stronger one or a coarser one, which is called numerical equivalence. So let me state the definition. So we say that two divisors are numerically equivalent if their intersection numbers with any third divisor are equal. So let's imagine that like we're going to say that a divisor D is 0 if D intersected with any other divisor is the number of intersection points is 0 in some sense. So this equivalence relation gives this numeric num of y, where y is our surface. Remember, x times x. And the intersection product kind of gives us a symmetric bilinear form. So num y times num y to z. So this is exactly why we needed to pass to numerical equivalence, to get a non-degenerate symmetric bilinear form. Because since we want to study intersection numbers, we better kill things which multiply with something to give 0. And we should say that is 0. So that's exactly what numerical equivalence is saying. I mean, to take it slowly again, we want to study the algebra of the intersections product. And if we just take the linear equivalence or just divisors as the traditional definition, then we may get that some non-zero divisor will intersect with all other divisors, and that being equal to 0. And we should kill those guys. And that's what numerical equivalence does. So in that case, by definition, this intersection product, by definition, gives a non-degenerate symmetric bilinear form, just because we've killed all things which product to 0. So we can now, a non-degenerate symmetric bilinear form is much better than something that is not. And there is a strong theorem called the Hodge index theorem, which describes how this symmetric bilinear form looks like. And I guess like in the language of motives, we're doing curves here. Y is a surface, of course. It's x times x. But anyway, in the case of curves, we are interested in the Hodge index theorem. But in the language of motives or like higher dimensional things, I guess here, what we standard conjecture, which is a conjecture still. The Wahl conjectures, of course, have been proven, but not via motives. The Wahl conjectures in the case beyond the curve have been proven, but not in the not through motives, even though like motives have been defined and things like this. But yeah, there's some standard conjectures which are still unproven. I mean, motivated by what is happening in the case of the curve. And if they were to be proven, then that would give like basically the original attempt proof of Walser's conjecture as a proof. So the Hodge index theorem basically says that this symmetric bilinear form, non-degenerate, it splits into dimension 1 positive definite form, and the other subspace being negative definite. So I guess in mathematics of what I just said, we need Sylvester's theorem, so that's why I take rationals here. You could take reals, it doesn't matter, but we certainly can't stay over Z because we need to kind of, we're relying on signature theorems here. But essentially, like the signature of this symmetric product, it looks, S is just a surface here, so S is Y. It just has dimension 1 positive definite, and the rest is negative definite, and that will be kind of what is crucial to get a handle on what we're trying to prove here, which is that these things have the right weight. I've given an example of like in the case of a quadric surface, and I've written the solution to this example in the appendix, so you can have a look at it. I think it's kind of important. Here's the solution. But let me just so that we get a better understanding of this Hodge index theorem, like take the quadric surface, S, Y, or S, or whatever in the notation. So the quadric surface is given by this embedding of P1 times, it's P1 times P1, of course, but this embedding it's not clear a priori that P1 times P1 is projective, but this embedding it gives it a subspace of P3, so it is projective. So anyway, there's this quadric surface that lives in P3, given by this embedding, and in this case, linear equivalence and numerical equivalence is actually the same, and it's just Z plus Z, and we can completely describe the intersection product. I mean, it looks like this, and in this case, you can verify by hand the Hodge index theorem. I mean, you can write down the matrix that this symmetric bilinear form is represented by, and the Hodge index theorem is just clear by hand. So let's apply it to our problem. There's this kind of this looks a little bit left field. I agree. Like this is basically the the crucial part for finishing off the proof of we're going to be using Hodge. We're going to be applying this index theorem to that lemma, I guess. But what I'm saying is to finish off proving this, we need to prove some kind of analysis statement. After one has proven this, there's a little bit of analysis to do, which we won't do. But essentially, this is the main kind of work, and that's what we'll do. So we're going to try and do this using Hodge index theorem. So let's try. So recall Y is X times X, our product, and we have two divisors on there. Let's call them H and V, which correspond to the horizontal and vertical lines, I guess. So H is X times some closed point X naught, fix some closed point, it doesn't matter. And X naught times X will be V. Of course, they're all linearly equivalent. I mean, for any other choice of X naught. If that's not clear to you, like, don't worry, like, please send me an email and we can set up we can either chat together or set up an extra video, and I'm happy to discuss and explain this in more detail. I mean, I'm assuming maybe one knows some divisors, but yeah, if you don't, it's okay. I'm happy to discuss and explain to you what that is outside of this lecture. So first thing is, like, the number of points at which H and V intersect is 1. It's just X naught times X naught. And the self intersection of H is 0. So these cannot be equal in numerical equivalence. And so we can define this finite dimension. So H and V are certainly different. So this gives some kind of finite. We can look at H, the subspace spanned in num Y of H and V, and we can write so num Y, rationalized as W, let's denote it by this. And we can write W as this subspace spanned by H and V, that's U. So it's the subspace spanned by H and V, and an orthogonal complement, U prime. So we can do it, we can take an orthogonal complement because the bilinear form is non-degenerate, symmetric bilinear. So there is such a thing as an orthogonal complement. And the claim is that the intersection form restricted to U prime is negative definite. So we're going to try and use the Hodge index theorem for that. So first of all, the matrix on U, with respect to that basis H and V, I mean, if you look at these intersection products, it's just 0, 1, 1, 0. And that basically is the same intersection product as in this example of the quadric surface. And this matrix has one positive eigenvalue. So by the Hodge index theorem, because the Hodge index theorem says that there's the subspace which it acts in a positive definite way is of one dimension, that means that the intersection form on U prime is indeed negative definite. So the hope is that like we can use some kind of Cauchy-Schwarz inequality or something to get some version of this statement. So we're almost there, like it's not too much more. So W again is our space num y rationalized. Everything is rationalized. I mean, we can't hope to work over Z, right? So let T be the operator which is pulled back by Frobenius. I mean, I'm just taking the map that was used here, right? I mean, I want to apply this map basically on the diagonal. I mean, because of this lemma, it's very natural to consider this map again. So T is a linear operator on num y, which sends divisors to the pullback of along this Frobenius. I mean, there is some subtlety here that like I'm kind of implicitly saying that a pullback is well defined, descends to numerical equivalence, and I mean that's true by something called the moving lemma. So I mean, you have divisors which are the equivalence relation is linear equivalence. Divisor is 0 if it's basically the divisor of a rational function. And there, when I take that quotient, one can kind of show that pullbacks and push forwards are pretty well defined between those things. And that that's kind of enough to show that the pullback is defined on the coarser numerical equivalence relation, which is what we're doing here. But I'll say something more about that in the next lecture. But in any case, just for now, take it for granted that like the pullback descends to numerical equivalence. So in this case, excuse me, I'll just get some water. I'll be back. So let's take a look at what the intersection product looks like when T acts on a divisor. So this bit here is like TD, and this is TE. Then, so I have like, there's some yoga that one can do, which is a pullback becomes a push forward on the other side. This is kind of like so here the difference between this side and this side is I'm putting the pullback to a push forward on the other side. And it's kind of like a standard proposition, I guess, like you can flip a pullback to a push forward when you swap the divisors. You don't need to do it as an exercise. It's kind of rudimentary. I guess I said as an exercise, but it's not that fun. But let's just take it for granted for now. I mean, it's kind of standard once you set up the theory. Then this pullback push forward is essentially capturing the degree of the Frobenius map, which is just PE. I mean, it's also another kind of standard proposition, which is this thing here, which is if I have a map phi, then the pullback push forward is given by, on the level of divisors at least, is given by the degree of phi. So at least like if phi is dominant or something like that. So the degree of the Frobenius, I mean, there's like Frobenius is x to the power of p. So there's like p sheets above the base. So you get PE here. And then by linearity of divisors, this p comes out and we get p of the intersection product. So in short, what's happened here is that we've defined some, which is the pullback of I Frobenius, and we've just shown that like the intersection product, when T acts on divisors, is just multiplication by P. Okay, so we're going to use this to get a handle on, well, prove that this statement here. I'm sorry that I'm moving up and down. I guess it can be a bit hard to kind of follow, but yeah. If people miss something or if people want me to go back somewhere, please let me know. I mean, there's like, yeah, doing lectures online, there's like a risk of going really quickly because everything is already written down. So yeah, to help me not go so quickly, please ask questions or please tell me to go back to places if you miss something. So yeah, we've just shown that like T acts by P on intersection products. We already know that like H intersects the diagonal in exactly 1 point and the V intersects the diagonal in exactly 1 point. So just to recall, H is the horizontal divisor and V is the vertical divisor. And of course they intersect the diagonal in exactly 1 point, which is just x naught times x naught. We've proven that like XFN, or the cardinality of the fixed points, is the intersection product of the diagonal with the graph of the Frobenius. That was the content of this lemma here. And this the graph of the Frobenius, I mean, by definition, it's just the linear operator T that we've defined here, acting composed n times on the diagonal. So wait, no, that was actually a statement. The fact that this graph of the Frobenius, the divisor of the graph is given by the pullback of the diagonal was one of the lemmas. This lemma here. So this lemma here, I mean, this is basically the operator T that we're looking at, and this is T to the N. So this value that we're interested in, it's the intersection product of the diagonal with the intersection product of the diagonal kind of twisted by T n times. So to evaluate what this looks like, let's write the diagonal as H plus V plus U prime. So where is this decomposition coming from? So again, like we're working in a rational vector space, and like H intersects the diagonal at 1 point. So H certainly has to lie at once here, and V intersects the diagonal at 1 point. So we certainly have to have a factor of V, and the rest U prime is coming from the orthogonal complement. So delta, this divisor, it lies in W here. So this divisor, think of it as an element in W, and I've just written it as something in U, which is H plus V, plus an element in U prime. So when you do that, so we can replace this by this factor here. And how does Tn act on each part? Well, Tn basically multiplies by P what it does to H, because how it acts on H is it's just multiplication by P. Because so if H is here, then we're basically taking Frobenius on X, because H is an full X factor on this side. So it gets multiplied by P. While on the other side, like for V, V has an X on the left-hand side, on the right-hand side, and its identity here. So T acts as identity on V. So for that reason, T acts on H by multiplication by P, and T acts on V by identity. So T to the N acting on this is like P to the N, which is where you get this P to the N, plus 1, because T acts on V, T leaves V invariant, so there's a plus 1. And then there's a Tn acting on U prime, which we're not sure what to do yet. So in short, we get P to the N plus 1, which is coming from this H and V intersection terms. And we get this funny looking thing, well, this abstract looking thing of Tn U prime intersected with U prime. So we're almost there. Like, I mean, we're trying to, just to remind you, we're trying to show that the cardinality of XPN is P to the N plus big O of P square root or to the N. So we've just shown that it has a Pn term. We just need to show that this term is, I mean, not much bigger than Pn over 2. And how we do that is, first of all, one notes that T leaves U prime invariant. So U prime is the orthogonal complement of H and V. And the fact that T leaves U prime invariant is pretty easy to show from this equality here. I mean, if you write down like V as something coming from U and another term coming from U prime, then because they're orthogonal complements, like you either get 0 or nothing. So essentially, like, because like T, preserves zeroness. I mean, like, if this is going to be 0, then this is going to be 0 as well. So yeah, it's a straightforward check to show that T leaves U prime by itself, like invariant. So this guy here lies in U prime. And recall that U prime is the intersection product is negative definite there. So we have an intersection product or some product between two elements in a negative definite space. So you can apply Cauchy-Schwarz inequality, basically, because it's negative definite. I mean, positive definite, negative definite, it doesn't matter, but like Cauchy-Schwarz now works. So in short, I mean, this term here by Cauchy-Schwarz looks like this. So you get Tn U prime intersected with itself and U prime intersected with itself. And Tn U prime is, I've written here for some reason, well, it's right, I hope, Pn over 2, but I'm not sure why that's the case. Let me see. So for some reason, Tn U prime times Tn U prime should be P to the power of N. I see. Because if you put in T U prime times T U prime here, you get P times U prime U prime. And if you do that n times, you get P to the N U prime U prime. And then you get two factors of U prime times U prime. And this U prime then comes out because there's a square root and you get Pn over 2. So it's just an application of this formula here. So anyway, like we've shown that this term here is big O of Pn over 2 because U prime was something fixed coming from delta X. So it's invariant. It doesn't depend on like any terms here. So just to summarize, like we've used intersection theory to count the number of points on the curve modulo Pn. Then that's like kind of intersection theory on linear up to linear equivalence. So that was enough. Then we've passed to numerical equivalence to grab more of a handle on what this looks like. And by grab more of a handle, we needed some kind of structure. So in particular, non-degenerate symmetric bilinear form. And that's the Hodge index theorem. And we passed to numerical equivalence there. That's very much related. The flavor of what's going on here is very much motive-like. I mean, in the next lecture, we'll look at like various different equivalence relations. In this case, we see that there is a certain advantage by passing to a coarser equivalence relation. I mean, we have access to something like the Hodge index theorem. And then, thanks to that Hodge index theorem, by doing some, I guess, algebraic manipulation, we see that the number of points on the curve, it looks like this. And then I guess you just have to take it for granted, or you can check yourself. But like once you have this statement, which looks, I guess, at first glance, rather far from what we're trying to prove, which is this weight term. So this is the hardest part of the Wahl conjectures. But once one proves this kind of analysis type statement, the kind of conjecture follows pretty easily. I mean, it's just like standard analysis, standard elementary analysis. But I agree that like it looks maybe at first glance a little bit fast still, but it's not apparently. But in any case, I don't want to discuss it because it's just standard analysis and it's kind of not what we're trying to do here. So yeah, I mean, that's the end of I guess, what I wanted to say for the first lecture. Are there any questions, or do people want to say something that I can improve for next time or something? Or if you don't want to say now, you can send it to me by email.
I think there are like no questions since everybody is so silent.
Okay. Well, thanks for joining me. And yeah, feel free to get in touch with me about anything, especially if devices are maybe not so clear. I'm very happy to take time to explain these things.
So do we have like lecture recordings? Do we have them, and where can we find them after the lecture?
That I'm not sure. I think this lecture was recorded. Let me check.
It says it is recorded, yeah.
Okay. Where can we find them? I'm not really sure. I mean, does someone have an idea, or?
There's a YouTube channel of the faculty, so I know how can you upload them there, but there are a few people who can do this, I guess, who have access to this channel and can upload like videos there. Okay.
In that case, let me ask someone who knows more than me, and I'm sure that I have the opportunity to upload this. I just hope that I don't need to like click somewhere where I need to save something explicitly, but so that I hope that when I leave this lecture that it's not lost or anything like that. I guess not. Just in case, like someone asked me like how we got the existence of polynomials pi. So the existence of these polynomials, like that's coming from Italca homology, essentially. So like what's happening here is that like this is like this rationality statement, like P1, P2, P3, P4, this will be like some kind of alternating product of different cohomology degrees in Italca homology. And these polynomials will be the characteristic polynomials of Frobenius operators on those Italca homologies. And you get an alternating sum, and that's why you get like this oscillating P1, P2, P3 thing going on. So I think in short, the existence of these polynomials is coming from Italca homology and the various machinery that comes with it. Okay, I guess like we'll end the lecture there, I guess. Thank you for coming, and have a great rest of the day.
Thank you for the lecture.
Thank you, it was clear.
Thank you.
Thanks.
Sorry, can you send the link on this notes in the chat?
Yes, I'll do that now.
Thank you.
Okay, thanks. And you have my email, so if there are any questions at all, please feel free to ask me. Okay, well, see you. Bye.